Here for all of you. Yeah, and how we can find the residue. For example, in case of removable singularity, it's trivially it's 0. In case of polar singularity, we have discussed that in the last class. For essential singularity, we cannot help. There is no formula that we can use, and means we just need to rely on the LoRa expansion, and that's about it. Okay, so here now before going into um, Cauchy residue theorem, I am going to need another concept, which is the concept of winding number. Okay, so winding number. So here, of course, let me first give you some examples so that it becomes more clear in your head what is exactly the winding number is. Okay, so let's draw a picture. So I'm going to give example in terms of the one summation integral of 1 over z, which we are used to do. Okay, so let's say this is circle of radius r, and this one, let's say, so therefore the circle has the equation r e power I theta. Theta varies between 0 to 2 pi or minus pi to pi, whatever you wish. Okay, and so let us call this path to be gamma r. Now we have seen already so many times integral over gamma r of 1 over z is what? Right, so this is what is the integral of 1 over z over gamma r. Okay, now in place of gamma r, let us take the following path. So let gamma r n be the same path r e power I theta, except that I vary my theta, let's say between 0 to 2 pi n. Okay, so here for instance at this moment I am taking n is bigger than or equal to 1. Okay, so this is what I take. Okay, so now of course when you see the picture of this path, you see that of course when you just look at the trace, it's only the circle. Okay, but what is happening is that I am taking theta from 0 to 2 pi n for any some integer bigger than or equal to 1. So therefore, what does this path really do? It traces the same path n times, right? Is it clear that this gamma Rn is effectively the same path traced n times, isn't it? Yeah.
Yes, sir.
Now, can you just do the integral and tell me what would be integral over gamma of Rn 1 upon z? What will be the integral?
2 and pi n.
Sorry?
Pi I.
2 and
2 pi n I.
I n I. So you see this n is featuring over here in the integral. Okay, so like you just need to calculate what is f of gamma t gamma prime t dt, and then if you integrate from 0 to 2 pi n, you are going to get 2 pi n I. Okay, so what you see is that just because the trace of two paths are the same, the integral need not be the same. Okay, so and depending on how the path is traced, your integral can change. Okay, so like I was telling you exactly that gamma Rn is the same path as gamma r but traced n times. Okay, so what we see is that somehow this n that I have over here, that n in some way it distinguishes gamma r and gamma n, gamma r and gamma r n, and also it distinguishes from like that really tells me that okay, even if the trace of the path is the same, there is something which is different. So this is what brings us to the concept of winding number. Okay, so effectively what I can say here, just as an English word, I can say that for instance, the path gamma r n winds around 0 n times. The simple path gamma r winds around 0 only once, and the path gamma r n is the same circle, but it's going to wind around 0 n number of times. Right? Is this clear to all of you?
Yes, sir.
Okay, so therefore, uh, remember, so this n I can write as 1 upon 2 pi I gamma r n of 1 upon z. Okay, so this n, which is, as I was telling you, that this is the number of times my path is winding around 0. That's the number which is reflected over here. So inspired by this phenomena, we take the following definition: winding number. Okay, so let gamma be a smooth closed curve. Of course, unless the curve is a closed curve, there is no meaning of talking about this winding thing. Like, at least for which point we want to talk about the winding number of a curve, I really need to have that segment of the curve to be closed. Okay, so like once you take out gamma from there, that particular point should be in a disconnected component. Like that connected component is going to be separate. Like for example, if I just have let's something like this, then maybe for points over here, I can still think of, okay, if I want to say that I want to restrict over here, and then I want to talk about winding number and all that, that could be one thing. But generally we will not take any curve which are like not closed. Okay, so really it will not make much of sense. So we are going to work with smooth closed curves. Okay, and of course you have seen already that for when I have a closed curve and I have a holomorphic function which is means a function which is holomorphic in the in the all the points which are somehow inside the curve. So then the integral is going to be 0, but that might not be the case in case of if I take non-holomorphic function like in this case. So of course we are interested to integrate over closed curves, and therefore as we said that there is this parameter winding number which is going to play some role in the integration. So we are going to define it for a smooth closed curve, and which uh, is, yeah, so that is what we are going to do. And so here let gamma be a smooth closed curve, and I take a complex number a belongs to C which is not on gamma. So that means the point does not lie on gamma, the trace of gamma. So then I define n gamma a to be the quantity 1 over 2 pi I integral over gamma 1 upon z minus a. Okay, so then this quantity is called the winding number of gamma around a. Okay, so from the example it is clear. For example, I can write gamma r has winding number 1 around 0, and gamma Rn has winding number n around 0. Yeah, so is the definition clear? The integral which, like for example, here I saw this integral gave me n. So that is the integral I am going to use to define the winding number of a curve gamma, smooth closed curve gamma, or piecewise smooth closed curve also you can take, closed curve gamma around a point A. Fine? Is this clear to all of you? Okay, fine. So this is what is the definition of winding number. And now, of course, I was telling you intuitively that that means from at least from this picture that this is really this n is really the number this curve is winding around n, like winding around 0 n times. Okay, so therefore here I would like to first of all say that this quantity winding number that I have defined, that should be actually an integer quantity. Okay, so there comes a theorem. Of course, you can ask me that why am I not saying that this is going to be a non-negative integer? For the following reason. You see, if I decide that my curve, winds, let's say, of course, I have said that generally we are going to take a positive orientation of a curve, that is anti-clockwise direction unless anything is said. But I may have a curve which, let's say, at some point, for a particular point, you may realize that this curve is winding in the clockwise direction, okay, or it's moving in the clockwise direction, and then for that particular curve the winding number could be negative. So just keep that in mind, because in that case, whatever the usual winding number you would imagine, but depending on the orientation of the path, because if you take in place of gamma tilde, you get a negative sign, right? So if your curve is, for a particular point, with respect to that point, if you see that the curve is on the clockwise direction, then you will know that your winding number is going to come out to be something which is negative. Okay, so yeah. Anyway, so the first thing that I would like to prove that this winding number is an integer. So for any smooth, as I have already told you, you can take piecewise smooth closed curve gamma, and a in C not in gamma, we n gamma a is an integer. Okay, so that's the first statement about winding number. So what do I have to show? I have to show that this integral takes integral integer values. Okay, so let us write it down. What is n gamma a? So n gamma a is 1 upon 2 pi I.
Hello.
Yes.
No,
Yes.
sir, A does not belongs to complex number.
Sorry. Yeah. Thank you. A belongs to complex number, not in gamma. Yeah. So n gamma a. Thank you. 1 upon 2 pi I integral over gamma 1 over z minus a. So this is what is the quantity which I need to figure out. Now, if I use the definition of path integral, I get this is 2 pi I integral. So let's say gamma is given by gamma t from 0 to up to 1. So this is 0 to 1 gamma prime t gamma t minus a dt. Okay, so here, of course, I am assuming generally, if nothing is said, gamma is from 0, 1 to c. Okay, so gamma is a closed curve anyway. Okay, so therefore, I need to show that this is an integer, and that means what I have to show is that the quantity. So we show that the quantity 0 to 1 gamma prime t gamma t minus a dt is an integer multiple of
2 pi I.
multiple of 2 pi I. Yes, exactly. Okay, fine. So what I do is that, of course, when I take integral from 0 to 1, I need to show that that's an integer multiple of 2 pi I. And, you know, you can imagine, like when I'm talking about 2 pi I, somehow the exponential is going to get related to this. Okay, so let's see how I'm going to do that. So define a function, define f from closed interval 0, 1 to c by f of x equal to integral from 0 to x gamma prime t gamma t minus a dt. Okay, so this is what I'm defining my f of x to. Okay, now why did I define it like this? See, the point is very simple, that you know this is the function which is a primitive of the function which is in the integral, which is the integrand. Okay, so this is how you have also done it, in case of means when I told you about fundamental theorem of calculus. So to get primitive, you can define this kind of function. So f is a primitive of this gamma prime x divided by gamma x minus a. So this is precisely what we have, and that means f prime of x is equal to gamma prime x divided by gamma x minus a. Okay, so I can try to simplify this, and I get f prime of x times gamma x minus a is equal to gamma prime of x. Okay, so this is what is over here. F prime x into gamma x minus a is gamma prime x. This is what I am getting. Okay, so that tells me gamma prime x minus f prime x into gamma x minus a is equal to 0. So this you see here, of course, this is almost in the form of f, means f, f times g, derivative of f times g, because here I have uh, gamma prime x, here I have gamma x minus a, here I have f prime. Okay, so it's almost in that form, except that some factor is missing. So what is that factor? That factor is, let's say if I multiply by e power fx, or let's say minus fx, this will be immediately crystal clear. Gamma x minus a equal to 0. Okay, so I can I get this one upon multiplying by e power fx. And remember one thing, that it's an if and only if condition, because the thing which I have multiplied, like I can also go back to the other step, because here exponential is anyway a non-zero function always, right? It never takes 0. So just by multiplying e power minus fx, this there will be no change. Like from this step to this step also I can go, because I know e power fx is non-zero. So therefore, this one now is in a closed form, right? By closed form, I means this is the derivative of e power gamma x minus a e power minus x fx. This derivative is equal to 0, and this is just a function of one variable. All I'm doing is a function of one variable. So gamma x minus a times e power minus fx is a constant. Okay, so I get this a constant function. Now I need to figure out what is this constant. So that's very obvious. You are just going to evaluate at a certain particular point. Let's say x equal to 0. Okay. So what is that point? So let's putting x equal to 0. What do I get? X equal to 0. We get gamma 0 minus a times e power minus f of 0. Now, what is e power minus f of 0? If you go back to the definition f of f, then f of 0 means integral from 0 to 0. So that means f of 0 is just 0. So e power minus f of 0 means e power 0, which is 1. So this is gamma 0 minus a. Okay, so this is precisely what I am getting. So that tells us what? So it tells us that e power minus fx gamma x minus a is actually gamma 0 minus a. This is what I'm going to get. Okay, and that means e power fx is gamma x minus a divided by gamma 0 minus a. Okay, so that means of course this is true at x equal to 0, but in general this is what I am going to get. Okay, fine, that's all right. So this implies what? What is e power f1? E power f1 is gamma of 1 minus a divided by gamma of 0 minus a. And just notice one thing, that of course all this quantity numerator is also non-vanishing because a is not in the path gamma. Now gamma is given to be a closed curve, right? So therefore gamma of 0 is same as gamma of 1, so this quantity is just 1. So that means it tells us that f of 1, e power f of 1 is equal to 1, and we have seen in case of exponential, so that the only kind of solutions that I can get is f of 1 is 2 pi I k for some k in z. Okay, so this shows hence n gamma a is 1 over 2 pi I into 2 pi I k, which is equal to k, which is in z. Okay, so slightly unintuitive proof, I will say. Okay, but like I said here, since you means whenever you need to have something like this with integer multiple of 2 pi I, you really need to somehow connect it to the exponential function. So or yeah, that kind of thing. So that completes the proof that this um, integral n gamma a, that's going to be always an integer. Okay. So fine, this is good. And now that we know that winding number is indeed is an integer, we are now going to understand certain, or like we are now going to see some properties of this winding number. Okay, so of course let's say I have a very complicated path. Let's say I have a very complicated path, so like the path could be spiral, it might be moving around so many times. So what we would like to do really is to try and understand how, like as I change the point, like let's say from this point I come to this point, I would like to understand what is the change in winding number. So we would like to understand that first of all. Okay, now for this, how do we do that? We are going to make certain remarks. Okay, so what are these remarks? Let's see. So of course, as I said, fix gamma. We are going to fix a curve gamma and vary a on c minus gamma. Okay, so c minus gamma means you just remove the image of gamma from c, and you are going to vary a on that. Okay, now once I have this, then my claim is that, so note n gamma a, so gamma is fixed and a is varying, like this quantity a is varying, so n gamma a is a continuous function on c minus gamma. So it's going to be a continuous function on c minus gamma. Okay, so how do I see this? So, for example, if I take, so let an be a sequence which converges to A, then if I consider this sequence of function fn of z, let's say, which is z minus an, then we can see, since an converges to A, we get fn converges to f uniformly. Okay, in fact, uniformly on whole of C rather, or C minus gamma, whatever you want to take. So fn converges to f uniformly, where f is z minus a. Okay, so this is just a triviality. You just take difference of fn and f. There's going to be difference of an and a. So this is what I'm going to get. And anyway, uniform convergence is, in fact, as I said, it's on whole of C. And these function, since this z minus a, that's a non-zero function on the curve gamma. So if z is in gamma, then it's 1 upon z minus an converges uniformly to 1 upon z minus a. Okay. So this is what we have, because of course here I am taking a sequence an, and an is converging to a, and a is something which is not on gamma. Okay, so gamma is anyway a closed curve, so it's a closed set, and a is a separate point which is not in gamma. So of course there will be a, an open wall around a, so which will not intersect gamma, and in that open wall, since ans are converging to a, all but finitely many ans will belong. So therefore this 1 minus 1 over z minus an, this will make sense, and this will converge uniformly to 1 by z minus a. And once I have this kind of uniform convergence, so integral uh, and limit and integral can interchange. So therefore, hence n gamma an converges to n gamma a. Okay. So once I have uniform convergence, I will get this. Okay. So now that I see this n gamma a is a continuous function on C minus gamma, so then I would be able to say something, some more precise statement about how the function in gamma a looks like. Okay. So is this clear to all of you that this is a continuous function on C minus gamma? Yeah? Yes or no?
Yes, sir.
Okay. So now here, first of all, so it's a continuous function and it takes values on the set of integers. Okay. Now remember, the function is not going from C, it's going from C minus gamma. So C is a connected set, but C minus gamma, especially since when gamma is a closed curve, C minus gamma will not be connected. Okay. But nevertheless, what I can say is that since the image of this function is in z, uh, we get that n gamma a remains constant on each connected components of C minus gamma. Okay, so I was drawing a picture. So like if my function is something like this, then sorry, like if my curve is like this, then you just take this is one connected component, this is one connected component, this is one, this is one, this is one. So what it says is that in all these connected components of C minus gamma, the value is going to be a constant value. Okay. Of course, we have to see what are the possible values that we can have. Okay. Of course, depending on, for example, in certain cases, I might loop around and then I can do something else. So it completely depends on which particular connected component we are in. But what we see is that across one fixed connected component, this value of n gamma a is going to remain the same. Okay, is it clear that
Yes, sir.
in one connected component this is going to remain the same? Okay, so in fact, I can just allude you to the following thing. Here what I have seen is that, for example, inside this I have z equal to 0, and this integral 1 upon uh, z is 2 pi I. But if you try to do this integral gamma r for any 1 over z minus a, for let's say mod a strictly less than r, so that means a is some point, let's say here inside, for this also the integral is going to come out to be 2 pi I. Okay, or if I take for example 1 over 2 pi I of gamma r of n, this quantity is also going to come out to be m. Okay, so it's not only that the integral over 1 over z of gamma r is equal to 2 pi I, but rather if you take any point which is inside this like which is covered by this circular region, or like any point, means you can clearly see here that c minus gamma r has two connected component. One is this unbounded one, and one is this interior of the disk, uh, set of all mod z less than or equal to less than r. So in that set, no matter what point you take, you are going to have the same winding number, and that is actually when I think of it as an in terms of the picture, that's very evident, right? Of course, I was telling you that gamma r n winds around 0 n number of times, but if I take any a for which mod a is less than r, for all these a's also, gamma r n winds exactly n times around that point, isn't it? Yeah, is it clear what I'm trying to say over here?
Yes.
Yeah. So this is what one key observation. Of course, I could have told you in the very beginning from this picture, but now that you understand that this as a function, this n gamma a as a function of a, it's a continuous function from c minus gamma to z. We see that any connected component you take of the set c minus gamma, there your n gamma a is going to remain constant. Okay, so this is what we understand. Okay, now there are two kinds of like connected components. Of course, certain connected components are going to be bounded, and there will be certain other connected components, one other connected component which is going to be unbounded component. Okay, so next remark is about the unbounded component. Okay, so consider the unbounded connected component of c minus gamma. Okay, so let's go back to the picture of 1 over z. So if I take some point in the unbounded connected component, so that means somewhere here, let's say this is my point a, or let's say write a prime for uh, convenience. So just purely from the perspective of winding number, tell me how many times do you think that this curve is winding around a prime, either gamma r or gamma r?
0.
0, exactly. So it's not at all winding around that, right? It's not winding around a prime. So
Yes, sir.
therefore, what we would like to actually establish is this: indeed, if I take any point in the unbounded component, I would like to show that this winding number there is actually going to be 0. So let us see how can I do that. So that's not very difficult for the following reason. So you see, it's an unbounded connected component. That means what? It's going to have, like, I can take my points in that component with large and large absolute value. Okay, so here, first of all, let A belongs to this component, unbounded connected component. So if I take A from there, we can choose A with arbitrary large modulus. Okay, I can do that. I can choose A with arbitrary large modulus. Now, what is n gamma A? N gamma A is 1 over 2 pi I integral over gamma 1 upon z minus A. Okay. Now, what does ML inequality tell us? That if I put an absolute value, I'll get an absolute value. This is going to be less than or equal to, let's say here I keep 1 over 2 pi. I have length of gamma, which is a fixed quantity anyway, once the gamma is given. Now, what do you think? What happens to this 1 upon z minus A? Provided, of course, my A does not belong to the set gamma. So, of course, like this quantity cannot grow to plus infinity. But I can take very large and large, values of A such that mod of A is very, very, very large. So this particular quantity, for example, whatever is your M, that M, so we can now, we can choose A such that, or let's say mod of A such that 1 by 2 pi L gamma times M, in absolute value, of course, this quantity in is less than 1. Okay, so is it clear to all of you that I can choose A in such a way that this quantity will be less than 1?
Yes, sir.
Because my M can be made arbitrarily small, right? Here A is in the denominator, as you can see.
Please repeat.
Yeah, so what I am saying over here is that here in the unbounded component, I have the flexibility of choosing this A arbitrarily large, right? Like I can take, for example, if somebody asks me that can you give me uh, a complex number in this unbounded component having modulus bigger than 10 billion, I will be able to give, right? That's what it means to say it's an unbounded component. Now, what I can see is that, let's say this is bounded above by M in general, or you can keep it MA if you like. Then my point is that I can make this, like, once you take, see, your gamma is fixed, so these choices of z, they are fixed, they are in a compact set, in fact, and this choice of A is in your hand depending on the point that you would like to check the winding number for. You can take like that particular A, and as you take A large and large, this quantity 1 upon z minus A, when you take its absolute value, that's going to go closer and closer to 0, right? Do you agree to that? Yes or no? So therefore, now I can choose A large enough so that this quantity, suppose your MA goes to 0, this 1 over 2 pi is fixed, L gamma is fixed. So this whole quantity is can be made less than 1. So that implies mod of n gamma A is less than 1. So what is the value of n gamma A from here?
0 because n gamma is integer.
Value. Very good. So since n gamma is an integer, so this quantity is 0. Now this is for some a, right? So for some a in the unbounded component, in the unbounded connected component. Now how can I say that in the whole of unbounded component n gamma a is going to be 0? How can I say that?
Z is also arbitrary.
No, here z is not arbitrary. Remember one thing, what did we show just now? I showed that this function remains constant on each connected components, right? And
Yes, clear.
the moment I got one point where the winding number is 0, I will get at all other points of the unbounded connected component, the winding number is going to be equal to 0. So, at all points of the unbounded connected component, we have winding number 0. Okay, so this is what I'm going to get. Okay, fine. So that's good. So precisely this is what I'm going to get. Okay, now here I can give you, for example, like pictorially. For instance, we saw this gamma r case. Okay, so this if this is gamma r, here the winding number is 1, and here the winding number is 0. Now, for example, if I take some curve like this, let's say. So let's say it goes like this, then like this, then like this, then like this. So here, what is the winding number? The winding number here is going to be 1. For here, the winding number is going to be -1, because of course it's going around those points once, but you can see that here the direction is clockwise, and here the winding number is equal to 0. Okay, outside. So like accordingly you will be able to get so many cases like that. Okay, so what we have understood is that on the unbounded connected component we can always say that the winding number is going to become 0, and each of the connected component is going to remain constant. Okay, fine. So now you see there is one topological notion which is the notion of simply connected domain. Okay, now this particular concept is actually very relevant in the context of complex integration theory. Okay, and for example, if you look at Conway's book, often they work with a simply connected domain, and that has an advantage that the integral, that means outcome of the integration, do not change. For example, if you are working in a simply connected domain, and then for some closed curve, let's say you have been able to uh, find out the integral, and you change the closed curve to another closed curve, the integral will not change. Okay, so this is what which we would like to have, this phenomenon. So of course now I cannot give you the theoretical definition of simply connected set, so that will require a bit of language, like talking about homotopy of paths and all that. Okay, but at this moment the way you can think of simply connected domains is domains with no holes. Okay, so I do not know how much you are going to study in topology course about all this, but if some of you have taken some algebraic topology course this semester, you probably already have seen some homotopy theory. Okay, so path homotopy and all that. So there, if any two paths are homotopy, then you call a domain to be simply connected. But let's say if we do not have any idea about simply connectedness, you can just imagine domains with no holes. Okay, so these are the domains which we are going to be interested about, and in fact we are going to uh, be interested about a particular property of simply connected domain. Okay. So the property is that if I take any holomorphic function on that domain, and if I have any smooth closed curve in that domain, then the integral of the holomorphic function over that closed curve should be equal to 0. Okay, so technically this is what I am looking for. Okay, so for example, uh, like um, as I said, I don't want to give uh, I don't want to talk explicitly about simply connected domains, but for example, I can tell you some examples. What are examples? Examples would be C is a simply connected domain. Any disk is a simply connected domain. Okay, so and for example, any half plane is a simply connected domain, or let's say any sector is a simply connected domain. And if I have to talk about non-examples, then I can tell you, let's say C minus 0. This is a non-example. Annulus is a non-example. So therefore, deleted neighborhood, uh, deleted neighborhood. These are not simply connected domains. Okay, so you can imagine that, like I said, there is some hole. So the hole need not be very big, but like it could be one point is missing. So those are the domains which are not simply connected. Now, why I am telling you about all this? For example, of course, we had seen that suppose I have a disk and disk D, and I have a function which is in holomorphic D. Then we saw that integral over gamma of f is 0 if gamma is a closed curve, closed curve D. But let's say I cannot just replace this disk by anything random. For example, I cannot take C minus 0. This is not allowed. For example, I can see that 1 over Z is holomorphic on C minus 0, but just keep this example in mind. So 1 over Z integral over gamma r is 2 pi I. Okay. So there is a significant difference like that is happening over here. The disk is giving that you take any holomorphic function, integrate over closed curve, you are getting 0. But here that's not happening. Okay. So the kind of phenomenon that I want to capture is the phenomena where we can say this kind of thing. So this is what uh, is a particular consequence, I would say, of simply connected domains. Okay, so if I here I have taken disk, but actually this can be seen, this exactly the same property, whatever I have written, the same property actually holds for any simply connected domain. Okay, so simply connected domain. So if I take any simply connected domain D, if you take any f in h of D, then integral of f over gamma is going to become 0. And the simple point, as I said, any two closed curve there are going to be homotopic. So in particular, any closed curve is going to be homotopic to a single point. Okay, so those of you who are doing algebraic topology course this semester, they will know probably this. And once you can, so there is a homotopy version of Cauchy's theorem, so which says that if you take two paths which are homotopic to each other, then the integral over those two paths are the same. And now, if I see that any closed curve is homotopic to 0 or a homotopic to a single point, then of course integral you just take integral over any single point, that's going to be a 0. Right, so therefore this simply connected domain is having this property So there is a background to it why that's true, but nevertheless you have this particular property on simply connected domains. Remember this again, whenever I say certain statements, those statements have certain hypothesis together with it. Okay, do not blindly apply any result for any particular set without verifying the hypothesis. Okay, do not blindly put, for example, that integral over any closed curve of any holomorphic function is going to be zero. That's not the case, right? It really depends where is your holomorphic function, where you are taking the closed curve and all that. Okay, so in fact, I don't. Let's not go into this simply connected domain any further, but rather I introduce a simple term for you, like so that you can remember this well. So I call these domains, let's say, closed curve domain. Okay, so what is a closed curve domain? Let's state what is that. So let D be a domain. Let D be a domain. We say D to be a closed curve domain. If for any holomorphic function f in h of D and a smooth closed curve gamma on D, integral of f over gamma is equal to 0. Okay, so that means wherever your closed curve theorem holds for holomorphic function, those kind of domains I'm going to call closed curve domain. Okay, so this is I'm just using it as a substitute for this simply connected thing. Okay. So for example, of course, any simply connected domain would be closed curve domain, like what I said. But if you, as I said, if you do not know about simply connected domains, there is no harm. You just, for example, consider this thing that you take you take D to be the set of all complex number, then you will know that it's a closed curve domain. You take your D to be unit disk or any disk for that matter. These are closed curve domains. Okay, so I have given you already examples. So the ones which I have given you over here, the same thing. Those things are going to apply. So C disk, half plane, sector, strip. If you take any strip, so all these are closed curve domains. Okay, so let's just keep it in this way. Let's not expand too much into this definition. All I am asking here is that if I have a holomorphic function, the integral should be equal to 0. Okay, so now once I have this definition in place, I am now in a position to state the Cauchy residue theorem. Of course, I have told you all the necessary backgrounds by now. Okay, so there was this simply connected thing which I am at this moment substituting it by closed curve domains. Okay, so what do I have? uh, let D be a closed curve domain, so I'm writing CCD. Okay, so let D be a closed curve domain, and if be a holomorphic function, a function on D, be a function on D which is holomorphic everywhere except except for isolated singularities at a sequence of discrete points. Okay, so I have isolated singularities for some. So it need not, I'm not saying that they need to be finite. Okay, so I can have infinitely many singularities. They are going to be just isolated singularities, and of course my domain need not be bounded, for instance. So I can have infinitely many singular points, let's say. So I have a closed curve domain. F is a function which is holomorphic everywhere on D, except uh, which is holomorphic everywhere except at isolated singularities at a sequence of discrete points Zn. So I call them Zn. Let gamma be a smooth closed curve or piecewise smooth, whatever you wish, smooth closed curve which does not pass through any of these Zns, does not pass through any of these Zns. Okay, so if I have time, I will try to tell you in case when you can, if you get some singularities on means on top of your contour, then how one deals with those things. I can try to tell you sometime later. Okay, but at this moment I am assuming that the path is not like none of these singular points lie on the path. Okay, so pass through any of these Zn's. Then the integral of f over gamma is going to be 2 pi I summation over n gamma Zn.
Sir, does not.
Sorry, it does not. Thank you. Residue f of z. Okay, so what am I saying? I'm saying that I have a smooth closed curve, and this curve is not passing through any of the singular points. Then the integral is nothing but 2 pi I summation over n. Actually there are two n's, so this n is the winding number. Okay, so summation n bigger than or equal to 1 n gamma zn residue f at zn. Okay, so that's Cauchy residue theorem for you. And here of course you can ask me that on the right hand side we have an infinite sum apparently, because my set of singular points could be infinite. Then do I have to talk about convergence of this infinite sum or not? Okay, but I would say that you really don't have to bother about convergence of this infinite sum, because actually all but finitely many terms in this infinite sum is equal to 0. Okay, so therefore there will not be any issue of convergence. So now can any one of you, or like now that I have told you the statement, can any one of you think why only finitely many terms here would be non-zero? Why do you think in this sum only finitely many terms would be non-zero? Yeah, any idea?
Because sir, f is holomorphic everywhere except at discrete point zn, मतलब मीन्स फाइनाइट टर्म्स की मतलब जो होंगे उन पे मतलब होमोमॉर्फिक नहीं है, और हर जगह है, तो जो रेजिड्यू आएगा वहाँ पे जीरो हो जाएगा वो.
नहीं, that's not the case. Residue तो बहुत सारे जगह पे हो सकता है. Like there could be infinitely many points where the function is not holomorphic. I am allowing that, so that is allowed. Okay. So for example, if I take something like 1 upon sine, right? So sine has zeros at n pi. So if I take 1 upon sine, that's going to have poles at n pi's, and all these are there. There will be infinitely many poles. All these are you know points where the function is not holomorphic. So it's allowed that you can have functions with infinitely many, and all these are discrete points. So you can have infinitely many singular points. That is allowed. Okay, but still I am going to have this infinite sum to be actually finite. Now that I have given you this example of 1 upon sine this function, so think of why this function, this infinite sum should be 0, rather like for why all but finitely many summands should be 0. Just imagine the case of 1 upon sine, and so you know that at n pi this has singularities, and now therefore you tell me why the summands all but finitely many of them will be 0. Roughly what you should try to think is that, see, when I have these infinitely many points, okay, which are perhaps which are points of singularity, only finitely many of them will be in some in the bounded connected components. Okay, in the bounded connected components I can have only finitely many of these singular points. So all but finitely many of them are going to lie on the unbounded connected component of C minus gamma. Okay, so therefore what will happen is that at those points the winding number is going to become 0, not the residue, but the winding number is going to become 0, and therefore for all but finitely many points your summand is itself is going to be 0. So is this clear what I am saying? Okay, so my point is that note the above
So,
sum. Yes.
so would gamma cover all those points? मतलब कि all those points are inside the gamma, then
No,
how
that
it would be?
no, that is not is given, right? I have not said anything like that. I have just said you have a like here of course it's a smooth closed curve on D, and you just have a sequence of discrete sequence of points. I have never said that D is going to encompass all these gamma zns. I have not said that. That's not going to be possible even, right? Because if this gamma encompasses all these like infinitely many singular points, then that's going to have a limit point, right? Isn't it?
Yeah,
So
yeah, sir.
I have never said that gamma is going to encompass these points. These singular points could be there, but like and all I am saying that none of these points are on gamma. That's all. Okay.
Okay, okay, sir. Clear.
Note the above sum is finite. So how do I see that? Precisely because only finitely many of these singularities are finitely many of these singularities can lie on the bounded connected component of connected components of C minus gamma. Okay, because if I do not take that, okay, so if there are infinitely many these singular points on the bounded components, then clearly means it's going to have a limit point, right? Any bounded sequence has a limit point in C. So therefore we are going to, but I am saying that this zns are a discrete set of points, like, and these are isolated singularities, so that's not going to be possible, so as otherwise they will have a limit point. Okay, so that's not going to be possible. So therefore all but finitely many of them are going to lie on the unbounded component, So yeah, finitely many of them can be on the bound. So all but finitely many of them are in the unbounded component. Hence n gamma a or zn is equal to 0 for all n except finitely. Okay, great. So this is precisely what we have. Okay, and okay, so uh, that's good. Great. So in fact, here for that matter of fact, you can assume f has only finitely many singularities, but in general, you can have infinitely many singularities. That is the point which I was trying to uh, make. Okay, so we are, of course, now going to work with only the finitely many of them, because we know that all but finitely many of them are going to lie in the unbounded component. Okay, so how do I prove this particular result? So proof, let z1 to zn be the only singularities. So I can rename them only if necessary, only singularities uh, lying inside the area enclosed by gamma. Okay, so of course we know there are only finitely many of such singularities. Okay, and denote. So all these are singular points. Okay, so therefore we know that these are isolated singularities. So we can write down LoRa expansion of f around each point, and you know which is the part which is responsible for, you know, zi is to be a singularity. The part is the principal part. Okay, so let denote pfzj to be the principal part of f at zj. Okay, then here one thing you need to observe is that then this pfzj is actually holomorphic for holomorphic at any zk for which k is not equal to j. Right? All of you agree to this? Because we also know, like the LoRa expansion that is there, that the, you know, the negative exponent part, that of course is not holomorphic at zj, but it's going to be holomorphic everywhere at every other point. Okay, because you see, when we have taken for example a LoRa expansion, like in general formal LoRa series, then what we have seen that the positive exponent, when you look at the positive exponent, namely the power series part, that power series part is convergent in a disk, and the part which is having negative exponent, that is actually convergent for some mod z bigger than rho, right? So it's rather so that part is convergent outside a disk, let's say. So effectively what it says that for most of the points actually the negative exponents, those part is going to be convergent. Okay, of course if you think of a LoRa series centered at certain point, of course those negative exponents are not going to be holomorphic there, but they're all going to be holomorphic anywhere outside, because at any other point, in fact you can just imagine, right? If I think of let's say z minus z1, then clearly this function is holomorphic at z1, z2. Similarly, z minus z1 square, that's also holomorphic at z2. And even if there are infinitely many terms, like in the Laura expansion around z1, I know about their uniform convergence. So therefore, when I sum all of them, they are still going to be holomorphic at z2. Okay. So the point is this principal part that's not holomorphic at z1, or like if I think of principal part at z1, that's not holomorphic at z1, but it's going to be holomorphic at all other for means at all other points, right? Is this clear to all of you? Yes.
Yes.
So now
Yes, sir.
what I want to do, of course, you should also realize that these principal parts are the problematic parts as far as we are concerned, like as far as if we concentrate only at zj. So for that particular point, the principal part is the problematic part. Okay, so what I'm going to do, we consider this new function. So consider g of z equal to f of z minus summation j from 1 to up to n is pfzj. I'm going to take this one. Okay, so then what it turns out that this the function g is a holomorphic function on D. Why? Because you take any point from on D, so that point, if it is not holomorphic, in fact, it's actually holomorphic for any zj for k not equal to j. Not only that, okay, it's holomorphic for any other point, right? So I should write it's holomorphic at any point z not equal to zj. I should write like this. Okay, so you take any point from z. So which suppose that point z is none of these z1, z2, zn. Then anyway, all these pf, zi's, they're all holomorphic at that particular point z. F is holomorphic at that particular point z. So therefore, the sum is holomorphic. Now you take a z which is among the z1 to up to zn. Then I know that f minus the principal part f at z1, let's say, that one is holomorphic at z1. Remaining all of them are holomorphic at z1. So G is holomorphic at z1. Okay, so take z from D. If z is not equal to zj for all 1 less than or equal to j less than or equal to n, clearly G is holomorphic. If z is equal to zj, write G as f minus p f zj, or let's write I over here, zi, because there are too many j's. I. Yeah. So suppose I have this, then you just subtract, first take subtract zi. So this becomes now holomorphic at zi plus, and then I have minus summation p f zj j from 1 to up to n, j not equal to I. So this is again holomorphic at zi. Is this clear to all of you? Yeah.
Yes, sir.
So therefore, what I see as a function, this g is holomorphic on D. Very nice. Now, if z g is holomorphic on D, I have taken G to be a closed curve domain. So that means, so if I integrate G over gamma, what am I supposed to get?
0.
I'm supposed to get 0. Very nice. Now I have this. So if integral of G over gamma is 0, that means integral of f over gamma is summation j from 1 to up to n integral p f zj over gamma. All of you agree to this? Yeah.
Yes, sir.
Now what is this integral? So let's write it down. Let's write down 1 p f zj. So 1 p f zj actually looks like starts from k equal to -1, and it can let's say go anywhere, can go up to anything. Just see, yeah, it can go up to anything, and then I have ak z minus zj power k. Okay, so I think this is up to
So minus infinity.
yeah, I have done that. So this is what precisely I have. So if I write, this is a minus 1 z minus zj plus a minus 2 z minus zj square plus so on and so forth. Okay, so this is precisely what I have, and remember this converges uniformly in a deleted neighborhood uh, uh, at zj. Okay, so uniformly convergent outside zj. So away from zj, this converges uniformly. So if I want to integrate over gamma, of course zj does not belong to gamma, so I am away from it. So this, sorry, not integral of f, but integral of pf zj. So therefore I can say this is, once I have uniform convergence, integral and this can be interchanged, and then I have integral over gamma z minus zj power k. Okay, so now tell me, if my k is let's say bigger than or equal to sorry, less than or equal to -2, what can I say about those integrals?
0.
Why?
Because we have proved it.
Yeah, so that was means primarily not only we proved, but there was an underlying reason. What was the reason? The reason was each of them had primitive, right?
Yes, sir.
Bigger than or equal to -2, each of the factor had primitives. So this is turning out to be a minus 1 integral over gamma 1 upon z minus zj. Now tell me, what is this quantity? This quantity, did we see just now
Yes,
in the
2
beginning of
pi
the
I.
2 pi I? No, no, not only 2 pi I. What is 2 pi I? Something else. See, what was winding number definition? Winding number is 2 pi I integral, sorry, winding number definition is 1 upon 2 pi I integral over gamma 1 over z minus a, right? Do not blindly put 2 pi I over there, because as I said, your curve could be traced twice at the same place, so you need to be careful. So this is, I have never said that this gamma is, just winding once. So this guy is 2 pi I times the winding number at zj times, of course, what is a minus 1? A minus 1 is the residue. Do I get this?
Yes, sir.
So therefore, hence I get integral of f over gamma is 2 pi I summation j from 1 to up to n gamma zj residue f at zj. Okay, so this completes the proof of Cauchy residue theorem. Is this clear to everybody?
Yes, sir.
Yeah.
Yes, sir.
So that's a very simple proof. Of course, here I am having, at the end I concluded with finite sum, but you already know that for other singularities they lie on the unbounded connected component. So you can in fact include this is some j bigger than or equal to 1. Doesn't matter. Really. Okay, so anyway, it's a finite sum always. Okay, so all you need to see that while calculating an integral of a function which is perhaps having some kind of singularity, all you need to see, look at the singularities of that particular function inside the curve that you have drawn. Okay, so within the curve, you will look at it. Is this clear to all of you? Effectively, that's what we need to look at. For other singular points, there could be several of them, but you really don't have to pay any attention. So when you take this kind of closed curve and contour integration along that, your main concentration will be on the points which are getting enclosed by this gamma. Okay, Abhishek, now do you see? So when, of course, those points are going to contribute to the integral, which are the singular points within the in the area enclosed by gamma, right?
Uh, yes, sir. So, but we take the whole complex plan, and as you give the example of 1/sin z, then all singularities belong to complex plan.
Yes.
Then what about them?
But when I will take a closed curve, let's say in C, that closed curve is going to enclose only finitely many of them, right? That's what is my point. Just think of any closed curve in C, it can only enclose finitely many points, isn't it? Because
Yes.
to give you a bounded domain effectively. Like when even if you try to imagine all the connected components, bounded connected components, that's a bounded set, and it cannot have infinitely many singular points because my singular points are discrete. They are isolated singularities. So my function is having those kind of points. So like I will not have any way, it's not possible to have that my singular points of singularities are going to, they could be infinite, but they are not going to have any limit point. Okay, so therefore in a bounded region I can only have finitely many singularities, right?
Yeah.
So yeah, so keep that in mind. So this is, I would say, one of the very most important statement in complex analysis, and this has a lot of applications we will see in coming few lectures. And remember, this one is a very useful tool whether you want to go for some competitive exams or even in mathematics. Cauchy residue theorem is something which is used in number theory in various topics. Okay, so this is so fundamental. And I will give some problem sets to do based on this Cauchy residue theorem and also whatever we have read so far. Okay, so that's all for today. My time is also up, and in case you have any questions, you can tell me. Otherwise, you can go ahead for next class.
So